A little bit ago we talked about a position equation or a position function, and then its derivative became something else or gave us some other information. You know, it turns out that we can take derivatives of derivatives. We can stack these things, these functions, and when I say stack, maybe that's the wrong word, but we can do this. We can take a function, we can take its derivative, and then we can take the derivative of the derivative. Now this is called the second derivative, or y double prime. If we're thinking of this as y prime, this is y double prime. We could take the derivative of this, and we would have y triple prime. You see, we would have the prime of that. And then we could take another derivative. And really, this then is called the fourth derivative of the original function. So derivative, derivative of derivative, derivative of derivative of derivative, and so on. And so we get now, and this can continue as far as we'd like to go. But as the notation for it beyond here is to use a parenthesis in whatever number we'd like to in here to indicate the level of the derivative that we're talking about. Notice the primes though here, and that symbolism, that notation would follow through. It's the same kind of notation if we were using function notation. That is, if f of x, we start with f of x, and the first derivative is f prime of x, and then the derivative of that is f double prime of x, and when we take the derivative of that, it means f triple prime of x, and when we go to the fourth level, we use a little 4 in parentheses. So that's the notation. There are a couple of other notations. You can look at those in your textbook, but we'll most frequently be using these notations. Now, when we get into these lower levels of derivatives, here's the kind of thing that can happen. We talked earlier about h of t as a height function, and we called it a position equation. In your textbook or in many textbooks, it's actually s of t. S is for the height. I'm using h for emphasis here. So it's a position function, and then its derivative function is a velocity function that we could call v of t. You see, velocity in terms of time. And the derivative of the velocity function gives a function which gives information about acceleration. So the second derivative of a position function is an acceleration function. The first derivative of a position function is a velocity function. So that's how these situations, these manipulations can come into play. Here's a problem involving the relationship between position, velocity, and acceleration. It says a ball is thrown into the air from the top of a 160-foot cliff. The initial velocity of the ball is 48 feet per second. Now, since 48 is positive, it means that the ball is being thrown upward. Now this implies that the position function is, and the position function is given here. Now this position function, by the way, is derived from a more general relationship from physics. It's actually from one of Newton's laws. We're not going to get into that here, but there is a sound basis for where this function comes from. At any rate, it says that the time t is measured in seconds, and we want to find the height, the velocity, and the acceleration of the ball when t is equal to 3. Now, to find the height, we use the position function, and all we do is replace t with 3 in the position function and evaluate. And when we do that, we find that the height is 160 feet. So we say that the height of the ball after 3 seconds is 160 feet. Now, velocity is the first derivative of position, and to understand that and why that's the case, just realize that derivative is rate of change in what you are taking the derivative of. So the velocity is the rate of change in position, you see, because we're taking a position equation, we're taking its derivative, so the derivative is the rate of change in position. And when we take that derivative of the position equation, we get negative 32t plus 48. Notice the notation here is I'm using s prime, and we could use the derivative of s with respect to t, a different kind of notation if we wanted to here. But at any rate, all we do is take this first derivative equation or function, and we replace t with 3 and evaluate, and we find that the velocity is negative 48 feet per second. And we say then that after 3 seconds the ball is traveling downward, and it's downward because of the negative business, at a rate of 48 feet per second. Now, for acceleration, For acceleration, we use the second derivative of the position equation. It's actually the derivative of the velocity equation, you see, because when we take the derivative of velocity, we are finding the rate of change in velocity. And rate of change in velocity, oh, that's acceleration, you see. And it's a rather trivial situation. Once we take the second derivative to be a negative 32, we know that then after 3 seconds and after any particular point in time, there's no variable t in it to change anything, so after any point in time, the acceleration, and this is an acceleration due to gravity, is 32 feet per second per second. So after 3 seconds, the ball is accelerating downward at a rate of 32 feet per second, or we could say 32 feet per second squared.